Hello there, and welcome to a quiet corner of the night, where we can let our minds wander backward through time. Not just a few hundred years, or even a few thousand. Tonight, we're going much, much further. We're going to step outside the bubble of human civilization entirely and ask a simple question that somehow feels enormous. What was the world like before any of this existed? Before cities and farms, before written language, before anyone sat around a fire and told the first stories? What was Earth like when it was truly, utterly wild? It's a strange thing to think about, isn't it? We're so used to the world as a human place, roads and buildings, agriculture and industry, borders and nations. Even when we imagine wilderness, we're usually picturing places that humans have at least visited, mapped, named. But for most of Earth's existence, none of that was here. No one was watching. No one was recording. The planet simply was, turning through space, hosting an ever-changing parade of life that had no idea what was coming next. And that's what makes this question so compelling, because the age before civilizations isn't just a blank space in history, it's the vast majority of the story. Human civilization, by any definition, is maybe 10 or 12,000 years old. Agriculture is perhaps slightly older. But Earth itself, 4.5 billion years. We are quite literally the last few seconds of a very, very long day. And tonight we're going to explore what happened during all those hours that came before we showed up. I should mention, if you're new here, that this is the kind of topic we love to sink into slowly. We're not racing anywhere. There's no quiz at the end. This is just a chance to let your imagination stretch backward into deep time and see what it finds there. If this resonates with you, if this kind of slow, curious exploration feels like your kind of thing, I'd be grateful if you tap the like button or subscribed. It helps this quiet little channel reach other minds that wonder about these things. No pressure, of course, just an invitation. So settle in. Get comfortable. Let the day's noise fade away for a bit, because we're about to take a journey not through space, but through time. And not just any time. We're heading into an age when the very concept of civilization would have been meaningless, when the Earth was sculpted by forces that had nothing to do with intelligence or intention, and when the creatures that walked, swam, and flew across this planet were following patterns that had been honed over millions upon millions of years. An age of ice and fire, of giants and silence, of transformation so slow and so complete that it's almost impossible to grasp. An age that in many ways made everything else possible. Let's begin with something that sounds simple, but really isn't. Time. Not the time we check on our phones or mark on calendars. Not even the time we measure in lifetimes or generations. We're talking about geological time, deep time, the kind of time that makes the entirety of human history look like the blink of an eye in a very long night. When we talk about history in the normal sense, we're usually thinking in terms of centuries or millennia. The Roman Empire fell about 1,500 years ago. The pyramids were built maybe 4,000 or 5,000 years back. The earliest known writing systems emerged around 5,000 or 6,000 years ago in Mesopotamia and Egypt, marking what we traditionally call the beginning of civilization. These feel like vast spans to us, and in human terms, they are. They represent dozens or hundreds of generations, entire cycles of empires rising and falling, of languages being born and dying, of human experiences accumulating like sediment. But in planetary terms, they're almost nothing, less than nothing. They're the thinnest possible film on the surface of something so much deeper that it defies comprehension. Earth is approximately 4.5 billion years old. Let me write that out so it doesn't just slide past, so you can see all the zeros. 4,500,000,000 years. 4,500 million years. 4,500,000 millennia. Try to picture that. Try to feel it. You can't, really. None of us can. Our brains simply aren't built to comprehend numbers that large in any meaningful way. We evolved to think in spans of seasons, of lifetimes, of perhaps a few generations if we're being ambitious. Geological time operates on scales that are not just larger than human experience, but larger in a way that makes comparison almost meaningless. But let's try anyway, because understanding the scale, even imperfectly, changes how we see everything that came after. It changes how we see ourselves. It changes what seems possible and what seems permanent. It gives us perspective that's both humbling and liberating. One way to think about it is to compress Earth's entire history into a single 24-hour day. If the planet formed at midnight, the first solid crust wouldn't form until around 1 or 2 in the morning. Life, the first primitive single-celled organisms, didn't appear until around 4 in the morning, after hours of cooling and chemical evolution. For most of the day, through morning and afternoon and into evening, life remained simple, microscopic, bacterial, invisible to any observer, if there had been one. Complex multicellular organisms, the first animals we'd actually recognize as animals, didn't show up until after 8 in the evening. The Cambrian explosion, that burst of diversity we talked about earlier, happened around 9 p.m. Fish appeared in the oceans around 9:30. Plants began colonizing land around 10. By 10:30, forests were established and arthropods were scuttling across the ground. Dinosaurs emerged around 11 p.m. and dominated the planet for over 2 hours of our compressed day, finally going extinct around 23 minutes before midnight. The entire age of dinosaurs, that 150 million year span that feels so ancient to us, represents less than 10% of Earth's total history, and it fits into about 2 hours of our 24-hour day. Mammals began to diversify and spread around 11:35 p.m. The ancestors of humans, early primates, appeared around 11:50 p.m. Our own genus, Homo, emerged around 11:58 and 30 seconds. Anatomically modern humans, Homo sapiens, appeared around 11:59 and 48 seconds. Agriculture was invented at 11:59 and 59 seconds. All of recorded human history, every empire, every war, every work of art and science and philosophy happens in the final fraction of a second before midnight. Think about that. Really sit with it for a moment. If Earth's history is a full day, we've been here for 12 seconds. Civilization has existed for 1 second. You could blink and miss us. Another way to visualize this is to imagine Earth's history as a timeline stretching from one end of a football field to the other, about 100 meters. Each meter represents 45 million years. At one end, Earth forms. For the first 22 meters, over 1 billion years, there's no life at all. For the next 60 meters, all life is microscopic and single-celled. Complex multicellular life appears at the 80-meter mark, 20 meters from the end. The Cambrian explosion happens at meter 83. Dinosaurs appear at meter 94 and go extinct at meter 98.5. All of human evolution, from the first members of our genus to the present, happens in the last 4.5 centimeters. All of human civilization fits in the last 1/4 millimeter. You'd need a microscope to see it on this scale. This is not a trick of perspective or a rhetorical flourish. This is literally how the numbers work out. We are incomprehensibly recent. The world we know, the world of humans and cities and technology, exists in a time span so brief compared to Earth's total existence that it barely registers. And yet, in that brief span, we've convinced ourselves we're permanent, we're central, we're what it was all leading to. We've forgotten, or never learned, that we're a recent arrival in an ancient house. It's humbling, and it's essential context for everything we're about to discuss. Because when we talk about the age before civilizations, we're not just talking about a few thousand extra years of prehistory. We're talking about an incomprehensibly vast span of time during which the planet was shaped by geology, climate, biology, and pure chance into something that could eventually support what we now call human life. The age before civilizations is, quite literally, almost all of Earth's existence. Civilization is the anomaly, the exception, the unprecedented thing. Deep time, the slow grinding transformation of rock and sea and sky, is the norm. So how do we even study this? How do we know what the planet was like millions or billions of years ago? The answer lies in the Earth itself, in the rocks beneath our feet, in the layers of sediment at the bottom of the ocean, in the ice that's accumulated at the poles, over hundreds of thousands of years. The planet keeps a record, not a perfect one, but good enough to reconstruct much of the story. The basic principle is called stratigraphy, the study of rock layers. Sedimentary rocks form when particles settle out of water or air, accumulating in horizontal layers with the oldest at the bottom and the youngest at the top. Over time, these layers are compressed and cemented into solid rock. If we can find a place where these layers are exposed, a cliff face or a canyon wall or a road cut, we can read them like the pages of a book. Each layer tells us something about the environment when it formed. A layer of sandstone suggests an ancient beach or desert. Shale indicates a muddy seafloor. Limestone forms from the accumulation of shells and coral in warm, shallow seas. Coal represents compressed remains of ancient swamp forests. Volcanic ash layers can be dated precisely using radiometric methods and serve as time markers that correlate across vast distances. Fossils preserved in these layers tell us what life was like, not just which species existed, but how they lived, what they ate, how they reproduced. The distribution of fossils tells us about ancient climates. Finding tropical plant fossils in Antarctica tells us the poles were once warm. Finding marine fossils on mountaintops tells us those mountains were once underwater before tectonic forces pushed them up. But fossils are rare. The conditions required for fossilization, rapid burial and protection from decay, are so specific that most organisms that have ever lived left no trace. We have fossils of perhaps 1% of species that ever existed, maybe less. And even those fossils are often fragmentary, a few bones here, a shell there. Complete skeletons are extraordinarily rare. So paleontologists have to be detectives, reconstructing entire animals and ecosystems from limited clues. Chemical signatures in rocks provide another line of evidence. The ratios of different isotopes, variants of elements with different numbers of neutrons, tell us about temperature, about the composition of the atmosphere, about biological processes. Carbon isotopes reveal whether ancient carbon came from inorganic sources or from living things, and if from living things, what kind? Oxygen isotopes in fossil shells indicate ocean temperatures. Sulfur isotopes tell us about volcanic activity. Ice cores drilled from Antarctica and Greenland contain trapped air bubbles that preserve actual samples of ancient atmospheres. The longest ice cores reach back about 800,000 years, and recently, scientists have found even older ice, up to 6 million years old, in special locations in Antarctica where ancient ice is preserved near the surface. By analyzing the air in these bubbles, scientists can directly measure carbon dioxide and methane levels from before humans existed, creating a baseline for comparison with today's rapidly changing atmosphere. The ice layers themselves, counted like tree rings, provide a year-by-year record of temperature and snowfall, creating an incredibly detailed picture of past climates. These records show the regular cycles of ice ages and interglacial periods, driven by subtle variations in Earth's orbit, with remarkable clarity. Ocean sediments provide an even longer record. Cores drilled from the seafloor contain the shells of tiny organisms called foraminifera that lived in surface waters and then sank after death. The chemistry of these shells reflects the temperature and chemistry of the ocean when they formed. By analysing core samples from different depths, which correspond to different times, scientists can reconstruct ocean temperatures going back millions of years. Some cores span the entire Cenozoic era, showing the gradual cooling from the hot greenhouse world of the early Eocene to the Ice Age conditions of the Pleistocene. Volcanic rocks provide yet another type of data. When molten rock solidifies, magnetic minerals within it align with Earth's magnetic field at that moment. Since Earth's magnetic field has reversed many times throughout history, switching north and south poles, these ancient magnetic signatures serve as time markers. Geologists can correlate rocks from different locations based on their magnetic orientation, creating a global chronology that spans hundreds of millions of years. Tree rings, while limited to the last few thousand years in most cases, provide extraordinarily precise annual records of climate conditions. Some living trees, like bristlecone pines, are over 4,000 years old. By overlapping patterns from living trees with dead wood preserved in dry environments, scientists have extended the tree ring record back over 11,000 years in some regions. Each ring's width and density reflects that year's temperature and rainfall, creating a detailed climate archive that can be correlated with ice cores and other records. Coral skeletons preserve similar information for tropical oceans. Like trees, corals add layers annually, and the chemistry of those layers reflects ocean temperature and composition. Fossil corals can be dated using radiometric methods and analysed to reveal ocean conditions hundreds of thousands or even millions of years ago. All of this data feeds into sophisticated computer models that simulate ancient climates. These models incorporate everything we know about how oceans circulate, how ice sheets grow and shrink, how atmospheric composition affects temperature, how continents drift and collide, how plants and animals affect their environments. By running simulations and comparing them to the evidence from rocks and ice and sediments, scientists can test hypotheses about what drove past climate changes and refine their understanding of how the Earth system works. The models aren't perfect. They depend on assumptions and simplifications. But they're constantly being improved as more data becomes available and computing power increases. And they're remarkably good at reproducing known past climates when fed the right inputs, which gives us confidence they're capturing something real about how the planet works. And gradually, through this painstaking process of observation, analysis and synthesis, a picture emerges. Not a complete picture. There are gaps, uncertainties, ongoing debates. There are periods where the rock record is sparse or ambiguous. There are questions about the timing and causes of major events. Science is always provisional, always open to revision as new evidence appears. But enough of a picture exists to see the broad strokes, to understand the major events, to recognize patterns and cycles. Enough to tell the story, even if many details remain unknown or contested. The story of Earth before civilizations is really the story of these transformations revealed through this evidence. It's about how a ball of molten rock spinning through space gradually cooled and stabilized enough to allow liquid water. How that water became the medium for the first simple life forms. How those life forms, over billions of years, transformed the atmosphere and the chemistry of the oceans. How continents moved and mountains rose and fell. How ice ages came and went. How life itself became more complex, more diverse, more strange. And how, in the very last instant of this immense saga, a particular lineage of primates developed the capacity for abstract thought and started wondering about where they came from. Ice cores drilled from Antarctica and Greenland contain trapped air bubbles that tell us about atmospheric composition hundreds of thousands of years ago. Ocean sediments preserve the shells of tiny organisms whose chemistry reflects the temperature and salinity of ancient seas. Volcanic ash layers can be dated precisely and correlated across vast distances. Even the arrangement of continents, which have drifted and collided and broken apart over hundreds of millions of years, leaves traces in the magnetic orientation of rocks and the distribution of similar fossils on now separated landmasses. It's detective work on a planetary scale. And what it reveals is astonishing. Earth hasn't been static. It hasn't been stable. It's been a dynamic, churning, transforming system from the very beginning, cycling through states that would seem utterly alien to us if we could visit them. Periods when the entire surface was molten. Periods when the whole planet may have been encased in ice. Periods when the atmosphere was toxic to anything we'd recognize as life today. And periods when the climate was so warm that forests grew in what are now the polar regions. The story of Earth before civilizations is really the story of these transformations. It's about how a ball of molten rock spinning through space gradually cooled and stabilized enough to allow liquid water. How that water became the medium for the first simple life forms. How those life forms, over billions of years, transformed the atmosphere and the chemistry of the oceans. How continents moved and mountains rose and fell. How ice ages came and went. How life itself became more complex, more diverse, more strange. And how, in the very last instant of this immense saga, a particular lineage of primates developed the capacity for abstract thought and started wondering about where they came from. We are the first chapter where the story becomes self-aware. But to understand that chapter, we need to understand everything that led up to it. We need to go back to the beginning. Imagine standing on the surface of Earth 4 billion years ago. If you could somehow survive there, which you absolutely could not. The ground beneath your feet would be hot, unstable, constantly reshaped by volcanic activity. The sky above would be an angry reddish-orange, thick with carbon dioxide, water vapor, methane, and ammonia, but almost no oxygen. The air would be unbreathable. The temperature would be scorching. Impacts from asteroids and comets would be relatively common, each one releasing energy equivalent to thousands or millions of nuclear weapons. This was the Hadean Eon, named after Hades, the Greek underworld, and the name is fitting. It lasted from Earth's formation about 4.5 billion years ago until roughly 4 billion years ago. During this time, the planet was still cooling from its initial formation when countless smaller bodies collided and merged in the young solar system, releasing tremendous heat. The surface was likely covered in molten rock for much of this period. Any solid crust that did form was thin and frequently broken apart by impacts or volcanic eruptions. There was almost certainly no life during the early Hadean. Conditions were simply too extreme. But the building blocks were being assembled. Water, delivered by countless icy comets, was accumulating. Volcanic outgassing was releasing gases that would eventually form a more stable atmosphere. Simple chemical reactions were occurring in the hot, mineral-rich waters that pooled in volcanic vents and shallow seas. Nothing alive? Not yet, but chemistry moving in interesting directions. By about 4 billion years ago, conditions had calmed somewhat. The late heavy bombardment, a period of intense impacts, was winding down. The surface was cool enough that a more permanent crust could form. Liquid water could exist as actual oceans, rather than instantly boiling away. This marks the transition into the Archean Eon, which lasted from about 4 billion to 2.5 billion years ago. The Archean Earth would still seem utterly hostile to us. The atmosphere remained oxygen-free, dominated by carbon dioxide and nitrogen, with significant amounts of methane. The oceans were likely acidic and rich in dissolved iron. The sky would have been hazy, and the sun, younger and slightly cooler than it is now, would have appeared dimmer. Yet something extraordinary happened during this time. life emerged. We don't know exactly when or how. The earliest evidence of life, traces of chemical signatures in ancient rocks from Greenland, dates to about 3.8 billion years ago, though this is debated. More certain evidence appears around 3.5 billion years ago in the form of stromatolites, layered structures created by communities of bacteria. These ancient bacteria were simple, single-celled organisms, but they were alive. They metabolized, they reproduced, they responded to their environment, and they began, very slowly, to change the planet. The most important change came from a particular type of bacteria that evolved the ability to perform photosynthesis. Cyanobacteria, as they're called, could use sunlight to convert carbon dioxide and water into sugars, releasing oxygen as a waste product. At first, this oxygen didn't accumulate in the atmosphere. It reacted with dissolved iron in the oceans, forming rust-colored bands of iron oxide that we can still see in ancient rock formations today. These banded iron formations are some of the most striking evidence of early life's impact on the planet. But eventually, around 2.4 billion years ago, something called the Great Oxygenation Event occurred. Evidence suggests the oceans became saturated with iron oxide over hundreds of millions of years of oxygen production. There was nowhere left for the oxygen to go except into the atmosphere. And so, gradually, the air began to change. Oxygen levels rose. For most of the life that existed at the time, this shift would have been catastrophic. Oxygen was toxic to the anaerobic organisms that had evolved in an oxygen-free world. Based on what we can infer from the rock record, they died in vast numbers or retreated to environments where oxygen couldn't reach them. Deep ocean vents, buried sediments, and other anoxic refuges where their descendants still survive today. But some organisms adapted. They evolved ways to tolerate oxygen, then ways to use it for metabolism. Aerobic respiration is far more efficient than earlier metabolic strategies, and it opened up new possibilities for complexity. Still, for the next billion years or so, life remained relatively simple, single-celled, microscopic, invisible to any observer, if there had been one. This long stretch of relative stasis is sometimes called the boring billion, though that name is somewhat unfair. Important things were happening. Eukaryotic cells, cells with nuclei and internal structures, were evolving. The supercontinent Rodinia was assembling and then breaking apart. And the planet was entering one of the most dramatic climate events in its entire history. Around 700 million years ago, something went terribly wrong or terribly right, depending on your perspective. The Earth's climate entered a feedback loop that may have pushed it toward a state so extreme that much or all of the planet became covered in ice, from pole to equator. This is the snowball Earth hypothesis, and while the details are still debated by scientists, and the exact extent of glaciation remains uncertain, the evidence for at least 2 major global glaciation events during this time is compelling. How does an entire planet freeze? The key is a process called ice albedo feedback. Ice and snow are highly reflective. They bounce sunlight back into space rather than absorbing it. So when ice begins to spread, it causes cooling, which causes more ice to spread, which causes more cooling. Normally, this process is limited by geography. Ice can only spread so far before it hits warm tropical oceans or land. But if conditions are just right or just wrong, the ice can keep spreading, feeding on itself, until it covers everything. Several factors may have contributed to these snowball Earth events. The sun was slightly dimmer than it is now, providing less heat. Volcanic activity may have decreased, reducing the greenhouse gases in the atmosphere. The breakup of the supercontinent Rodinia may have altered ocean currents in ways that disrupted heat distribution. And once the ice started spreading, it became self-perpetuating. Picture it. A planet encased in ice, glaciers covering the continents and sea ice spreading across the oceans, temperatures plunging far below freezing almost everywhere, life, which by this time had begun to diversify and spread, suddenly confined to a few refugees. Maybe in hot springs, maybe near volcanic vents on the ocean floor, maybe in thin layers of liquid water beneath thick ice, similar to what might exist on Jupiter's moon, Europa today. It would have been a near-extinction event, one that erased much of the progress life had made. And yet, paradoxically, Snowball Earth may have set the stage for the explosion of complex life that followed. Because ice, as impenetrable as it seems, isn't permanent. Volcanoes don't stop erupting just because the surface is frozen. They keep releasing carbon dioxide into the atmosphere. Normally, carbon dioxide is removed from the air by weathering of rocks and absorption by the oceans. But with everything frozen, these processes slowed or stopped. Carbon dioxide accumulated. It may have taken millions of years, but eventually, the greenhouse effect from all that accumulated carbon dioxide overcame the ice albedo feedback. The planet began to warm. The ice began to melt. And once it started melting, the process accelerated. Dark ocean and land replaced reflective ice, absorbing more sunlight, warming further. Earth swung from a frozen wasteland to a hot, carbon dioxide-rich greenhouse in a relatively short period of geological time. This rapid environmental change, combined with increased oxygen levels from photosynthetic organisms, may have created conditions that favored the evolution of more complex life. And indeed, shortly after the last Snowball Earth event, around 540 million years ago, something remarkable happened. For 3 billion years, life on Earth had been mostly microscopic and simple. Single-celled organisms dominated. Even after multicellular life emerged, around 600 million years ago, most organisms were still relatively simple, soft-bodied creatures that left few fossils. There were sponges, jellyfish-like animals, strange quilted organisms unlike anything alive today. They carpeted the seafloor, filtered nutrients from the water, reproduced and died, and the world remained, by our standards at least, quiet and uncomplicated. Then, in a geological instant, everything changed. This is known as the Cambrian explosion, and while explosion might sound dramatic, in geological terms, it was extraordinarily rapid. Over a period of perhaps 20 or 30 million years, starting around 540 million years ago, most of the major groups of animals that exist today first appeared in the fossil record. It was a burst of evolutionary innovation unlike anything before or since. Suddenly, or at least suddenly by Earth standards, the oceans were full of creatures with shells, with eyes, with segmented bodies, with specialized appendages for walking, swimming, grasping, cutting. The fossil record, which had been sparse and dominated by simple forms, suddenly exploded with diversity and complexity. Trilobites, those iconic fossils that look like ancient armored bugs, appeared and rapidly diversified into thousands of species. They had compound eyes, articulated legs, the ability to roll into defensive balls. They were segmented, like modern arthropods, with distinct body regions and specialized appendages for different functions. Alongside trilobites came the ancestors of modern arthropods, early ancestors of crustaceans, with jointed legs and hardened external skeletons. Anomalocaris, a predator up to a meter long with grasping appendages and a circular mouth ringed with teeth, one of the top predators of its time. Upobinia, with 5 eyes and a long, flexible proboscis. Hallucigenia, which puzzled scientists for decades because it was so strange they couldn't even figure out which way was up, with spines along its back and tentacles along its sides. Mollusks appeared, the group that today includes snails, clams, squids, and octopuses. Early forms had simple cone-shaped shells. Brachiopods, superficially similar to clams but belonging to an entirely different group, became abundant. Echinoderms, the group that includes starfish and sea urchins, evolved their distinctive five-fold symmetry, and crucially, the first chordates appeared, animals with a stiffening rod running along their backs, the ancestors of all vertebrates, including eventually us. Why did this happen when it did? It's one of the great questions in evolutionary biology, and there's no single agreed-upon answer. Multiple factors likely contributed, though scientists continue to debate their relative importance. Increased oxygen levels certainly played a role. The Great Oxygenation Event had occurred billions of years earlier, but oxygen levels had remained relatively low through much of Earth's history. Around the time of the Cambrian explosion, oxygen levels rose significantly, possibly reaching 50 to 70% of modern levels or higher, based on geochemical evidence. Complex multicellular life requires more energy than simple single-celled life, and aerobic metabolism, which uses oxygen, provides that energy far more efficiently than anaerobic metabolism. Higher oxygen levels made it energetically feasible to grow larger, to move faster, to build complex structures like eyes and brains. The evolution of predation may have created an evolutionary arms race, though this interpretation is still discussed among researchers. Once some animals developed the ability to actively hunt and kill others, prey species faced intense selection pressure to develop defenses, shells, spines, the ability to move quickly or hide effectively. And predators in turn face pressure to become better at hunting, evolving better sensory systems, faster movement, more effective weapons. This back and forth could have driven rapid adaptation and diversification. Changes in ocean chemistry made it easier for organisms to build shells and skeletons. The oceans became more saturated with calcium carbonate, the mineral that makes up shells and bones. This may have been related to changing patterns of weathering on land as continents moved and eroded, releasing more calcium into the oceans. Once hard parts became possible, they offered tremendous advantages: protection from predators, support for larger bodies, points of attachment for muscles, and hard parts fossilize far more readily than soft tissues, which is part of why the Cambrian fossil record is so much richer than what came before. The innovation may have been happening earlier, but without hard parts, it didn't leave much trace. The breakup and reformation of continents may have created new ecological niches. As Rodinia broke apart and new ocean basins opened, new environments were created, shallow continental shelves where sunlight penetrated and nutrients were abundant. These productive environments may have provided opportunities for ecological diversification. There's also the concept of developmental toolkits. All complex animals share a set of genes called Hox genes that control body plan development, determining which parts of an embryo become which parts of the adult body. These genes may have evolved relatively early, in the late Precambrian, but it took time for evolution to explore all the possibilities they offered. Once the toolkit was in place, evolution could rapidly generate new body plans by tweaking the expression of these genes, turning them on or off in different places or at different times during development. Or perhaps life simply reached a tipping point where the basic mechanisms for complexity, the genetic and developmental systems, the cellular structures, the ecological interactions, were finally in place and could be rapidly explored in many different directions at once. Like a dam bursting, once certain thresholds were crossed, change became rapid and self-reinforcing. Whatever the cause or combination of causes, the result was transformative. Earth went from a world of microbial mats and simple multicellular organisms to a world of ecological complexity. Food webs became intricate networks with multiple trophic levels. Predators hunted prey. Prey evolved defenses. Scavengers fed on the dead. Parasites evolved to exploit living hosts. competition and cooperation both became important evolutionary forces. And crucially, over the next 100 million years, life moved onto land, conquering the one major environment it hadn't yet colonized. The first plants appeared perhaps 470 million years ago, simple mosses and liverworts clinging to rocks and soil near the water's edge. These early land plants faced tremendous challenges. They needed to support themselves without the buoyancy of water. They needed to transport water and nutrients from the soil to their tissues without drying out. They needed to reproduce without water to carry their gametes. Over millions of years, plants evolved solutions to all these problems. Vascular plants, with specialized tissues for transporting water and nutrients, appeared around 420 million years ago. Roots allowed them to anchor firmly and access water deep in the soil. Leaves increased surface area for photosynthesis. Eventually, seeds evolved, protecting embryos and providing them with stored food, allowing plants to reproduce far from water. By about 400 million years ago, the first forests were beginning to grow. These forests looked nothing like modern forests. They were dominated by giant club mosses and horsetails, primitive plants that today exist only as small understory species, but in the late Devonian period grew to enormous sizes, some reaching heights of 30 meters or more. Their trunks were supported not by wood, but by thick bark, and they reproduced through spores rather than seeds. The landscape would have seemed alien, full of towering plants that don't exist in such forms anymore, with no flowers, no grass, none of the familiar vegetation of today. Animals followed plants onto land. First came arthropods, ancestors of modern insects, spiders, and millipedes. Early millipedes, some over 2 meters long, munched on dead plant material. Scorpions, among the first predators on land, hunted other arthropods. Eventually, insects evolved, diversifying into the most successful group of animals ever to exist, with more species than all other animal groups combined. Then came the vertebrates. Fish had evolved in the oceans, developing jaws, paired fins, and eventually internal skeletons made of bone. Some lineages developed lungs, allowing them to breathe air, useful in warm, shallow waters where oxygen levels could drop. Some developed muscular lobed fins that could support their weight, useful for moving through dense vegetation or across mudflats between pools. Around 375 million years ago, some of these fish began venturing onto land. Tiktaalik, one of the best-known transitional fossils, shows a mix of fish and tetrapod characteristics. It had fins with bones that correspond to the upper arm, forearm, and wrist of land vertebrates. It had a mobile neck, unlike most fish. It had lungs and gills. It could probably prop itself up on its front fins and drag itself across mudflats, though it certainly spent most of its time in water. Over millions of years, fish evolved into amphibians, fully capable of walking on land but still tied to water for reproduction. Early amphibians were diverse and successful, ranging from small salamander-like creatures to massive predators several meters long. Eventually, reptiles evolved, with eggs that didn't need to be laid in water, skin that resisted drying out, and more efficient lungs and circulatory systems. They could live their entire lives on land, and they rapidly diversified to fill ecological niches all over the world. And then came the dinosaurs. But before we get to them, we need to understand something important. These transitions, fish to amphibians to reptiles, took tens of millions of years. They involved countless intermediate forms, most of which left no fossils. Evolution doesn't leap from one form to another overnight. It proceeds through gradual changes, generation by generation, guided by natural selection acting on random variation. The fossil record gives us snapshots of this process, preserved moments in a continuous transformation. And what those snapshots show is a world constantly changing, constantly experimenting, constantly becoming something new. The Mesozoic era, often called the Age of Dinosaurs, lasted from about 250 million years ago to 66 million years ago. It's divided into three periods: the Triassic, Jurassic, and Cretaceous. And during this enormous span of time, Earth was a fundamentally different place than it is today. First, consider the climate. There were no polar ice caps. None. The world was much warmer on average than it is today, with temperatures perhaps 10 to 15 degrees Celsius higher. Carbon dioxide levels in the atmosphere were several times higher than pre-industrial levels. This created a powerful greenhouse effect that kept even the polar regions relatively mild. Forests grew where Antarctica now lies, beneath miles of ice. Crocodilian relatives lived in the Arctic. The geography was also dramatically different. At the start of the Mesozoic, all the continents were joined into a single supercontinent called Pangaea. Over time, Pangaea broke apart. North America separated from Europe and Africa. South America split from Africa. India drifted north toward Asia. These moving continents carried their flora and fauna with them, leading to distinct evolutionary paths in different regions. In this warm, lush world, dinosaurs thrived. They evolved into an astonishing diversity of forms. Massive sauropods, plant eaters with long necks and tails, some weighing as much as 70 or 80 tons. Armored ankylosaurs with club-like tails. Horned ceratopsians like Triceratops. Duck-billed hadrosaurs that may have lived in herds. And the predators. Allosaurus, Spinosaurus, and of course, Tyrannosaurus rex, one of the largest terrestrial predators that ever lived. But dinosaurs weren't the only creatures of the Mesozoic. The oceans teemed with marine reptiles like ichthyosaurs, which looked remarkably like dolphins, and plesiosaurs with their long necks and paddle-like limbs. Pterosaurs ruled the skies, flying reptiles ranging from sparrow-sized creatures to giants like Quetzalcoatlus with wingspans of 10 meters or more. Early mammals scurried in the underbrush, mostly small and nocturnal, staying out of the way of the dominant reptiles. And birds, which evolved from small feathered dinosaurs, were beginning to diversify. Life during the Mesozoic would have seemed alien to us in many ways. The vegetation was different. Flowering plants didn't appear until the Cretaceous, so for much of the era, landscapes were dominated by ferns, cycads, and coniferous trees. The air was thicker, richer in oxygen during some periods, which may have allowed insects to grow to enormous sizes. The days were slightly shorter because Earth's rotation was faster, and the moon was closer, making tides more extreme. It's hard to overstate how long this age lasted. 66 million years for the Cretaceous period alone. More than 3 times longer than the entire Cenozoic era, which includes everything from the extinction of the dinosaurs to the present day. T-Rex lived closer in time to us than it did to Stegosaurus. The dinosaurs weren't a brief phase. They were the dominant form of terrestrial life for over 150 million years. And then, suddenly, most of them were gone. 66 million years ago, an asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear weapons. It created a crater over 150 kilometers wide. It vaporized rock and sent debris shooting into space. Some of that debris fell back to Earth as a rain of superheated particles that ignited fires across the planet. The impact itself triggered massive earthquakes and tsunamis. Dust and soot filled the atmosphere, blocking sunlight and plunging the planet into a years-long impact winter. Photosynthesis stopped or slowed dramatically. Plants died. Herbivores starved. Carnivores had nothing to eat. Food chains collapsed. And in a geological instant, perhaps only a few tens of thousands of years, roughly 75% of all species on Earth went extinct. All the non-avian dinosaurs died. The pterosaurs vanished. the large marine reptiles were gone. Many plants and smaller animals disappeared, but not everything died. Birds, the descendants of small feathered dinosaurs, survived. So did some reptiles, including crocodiles and turtles. Mammals, still small and relatively insignificant, made it through. Fish and amphibians persisted. Many invertebrates survived. And slowly, over millions of years, life began to recover and diversify in the empty ecological niches left behind. This marks the beginning of the Cenozoic era, the age we still live in today. And with the dinosaurs gone, it was mammals that inherited the Earth. In the immediate aftermath of the extinction, the world was quiet and empty. The great herds of hadrosaurs were gone. The tyrannosaurs that hunted them were extinct. But in the forests and grasslands that gradually recovered, small mammals began to emerge from the shadows where they'd spent the entire Mesozoic. Without competition from dinosaurs, mammals diversified rapidly. Within 10 million years, a blink in geological time, they had evolved into forms ranging from rodent-sized to rhino-sized. Within 20 million years, whales had returned to the oceans, evolving from land-dwelling ancestors into fully aquatic creatures. Bats had taken to the air. Primates, our own lineage, were appearing in tropical forests. The Cenozoic is often divided into periods, but the key thing to understand is that it represents a long, gradual cooling trend. The hot greenhouse world of the Cretaceous slowly gave way to something cooler. Ice began to accumulate at the poles. Antarctica, which had been warm and forested, gradually froze over as it drifted to its current position over the South Pole, and ocean currents shifted to isolate it. By about 34 million years ago, permanent ice sheets had formed on Antarctica. This marks the beginning of what's sometimes called the Late Cenozoic Ice Age, which we're technically still in today. Over the next 30 million years, the climate continued to cool, fluctuating between warmer and cooler periods, but generally trending downward in temperature. Grasslands expanded as the climate dried and cooled. Forests retreated, and the animals adapted. Horses, which had been small forest-dwelling browsers, evolved into the larger, faster plains dwelling grazers we're familiar with. Large grazing animals like bison, antelope, and elephants spread across the continents. And predators evolved to hunt them: large cats, wolves, bears, and other carnivores. Around 2.5 million years ago, the cooling trend accelerated into what we call the Quaternary Ice Age, or simply the Ice Age, though technically it's just the most recent phase of the Late Cenozoic Ice Age. This is the period where our story really begins to focus, because this is when humans evolved. The Pleistocene epoch began 2.6 million years ago and lasted until about 11,700 years ago. This is the age of ice, of mammoths and saber-toothed cats, of giant ground sloths and dire wolves. This is when Earth became a place of dramatic climate swings, cycling between glacial periods, when ice sheets covered much of the northern continents, and warmer interglacial periods when the ice retreated. And it's during this time that megafauna, massive mammals, unlike anything alive today except perhaps elephants and rhinos, came to dominate ecosystems around the world. These cycles were driven by small variations in Earth's orbit, an axial tilt, known as Milankovitch cycles. Earth's orbit isn't perfectly circular, it varies slightly between more circular and more elliptical over a cycle of about 100,000 years. The tilt of Earth's axis varies between about 22 and 24.5 degrees over a cycle of 41,000 years. And the axis wobbles, precesses like a spinning top, completing a full cycle every 26,000 years. Each of these variations is tiny, but together they change the amount and distribution of sunlight reaching different parts of the planet. particularly the high northern latitudes where most landmass is concentrated. When the orbital conditions are right or wrong from the perspective of ice, summers in the far north become cooler. Snow that falls in winter doesn't fully melt in summer. It accumulates year after year, compressing into ice under its own weight. Ice sheets begin to grow, spreading outward from centres in Canada, Scandinavia, and northern Europe. The ice is bright white, reflecting sunlight back into space, cooling the climate further. More ice forms. The positive feedback loop continues until ice sheets up to 3 kilometers thick cover vast areas. During glacial maxima, the peak of ice ages, ice extended as far south as New York, covering all of Canada and much of the northern United States. Similar sheets covered northern Europe and Asia. So much water was locked up in ice that sea levels dropped by over 120 meters, exposing land bridges between continents. The Bering Strait between Alaska and Siberia became dry land, allowing animals and eventually humans to migrate between Asia and North America. The English Channel disappeared, connecting Britain to continental Europe. Indonesia became part of the Asian mainland. The geography of the world was dramatically different. And then, when orbital conditions shifted again, summers became warmer. Ice began to melt faster than it accumulated. Sea levels rose, land bridges flooded. The ice retreated, sometimes catastrophically, with massive glacial lake outbursts that sent walls of water racing across continents, carving out dramatic landscape features that remain visible today, like the channeled scablands in Washington state. These cycles repeated roughly every 100,000 years throughout the Pleistocene, with shorter variations on 41,000-year and 23,000-year cycles superimposed on top. The world pulsed between ice and relative warmth, never quite stable, always in transition. And life adapted. The world during the Pleistocene was a patchwork of ecosystems, unlike anything today. In the ice-free regions of North America, vast grasslands and tundra supported herds of massive herbivores that make modern bison look small. Woolly mammoths, the most iconic of these creatures, stood up to 3.5 meters tall at the shoulder, with the largest males weighing as much as 6 to 8 tons, comparable to the largest African elephants today. But unlike modern elephants, they were covered in thick fur, with an outer layer of long coarse guard hairs up to 90 centimeters long, and a dense undercoat that provided insulation. They had a layer of fat up to 9 centimeters thick beneath their skin. Their blood even contained a special variant of hemoglobin that functioned better at low temperatures, helping oxygen circulate even when it was far below freezing. Their most distinctive feature was their enormous curved tusks, which could reach 4.5 meters in length and weigh over 45 kilograms each. These weren't just for show. Mammoths used their tusks to sweep snow aside to reach the grasses beneath, to strip bark from trees, to dig for minerals, and probably to compete with other mammoths for dominance and mating rights. Where patterns on tusks show they were heavily used tools, worn down and sometimes broken through daily activities. Alongside the woolly mammoths lived their relatives, the mastodons, members of a different lineage of proboscideans that had been in North America much longer. Mastodons were slightly shorter, but equally massive, with straighter tusks and teeth adapted for browsing on leaves and branches rather than grazing on grass. They preferred forested areas and wetlands, complementing mammoths who favored open grasslands. In more southern regions, Columbian mammoths, larger than woolly mammoths and less hairy, occupied warmer grasslands, extending as far south as Central America. Giant ground sloths, members of several genera, were among the strangest megafauna. Unlike the small tree-dwelling sloths of today, these were massive terrestrial animals. Megatherium, the largest, reached heights of 3 to 4 meters when standing on its hind legs to reach tree branches, and weighed as much as 4 tons. They had powerful forelimbs with massive claws, perfect for pulling down branches, but also formidable defensive weapons. Cave paintings from Patagonia suggest some may have had coarse reddish fur with lighter patches, though most left no soft tissue evidence. Glyptodons, distantly related to armadillos, looked like massive armored vehicles. They were encased in a bony shell made of over 1,000 individual plates fused into a rigid dome that could be 2 meters long. The tail was armored as well, and in some species ended in a club-like mass studded with bony spikes, similar to an ankylosaur. They grazed on grasses and plants, protected by armor that few predators could penetrate. And there were predators in abundance. Smilodon, the saber-toothed cat, came in several species, with the largest Smilodon populator from South America, weighing up to 400 kilograms, comparable to a male lion but more heavily built. Their massive canines, up to 28 centimeters long including the root, were not for biting and crunching bone like the teeth of modern big cats. They were precision stabbing weapons, laterally flattened and serrated along the edges. Smilodon would ambush prey, using its powerful forelimbs and claws to wrestle them to the ground, then deliver a devastating bite to the throat or abdomen, using its gape of over 90 degrees to avoid hitting bone. The bite would cause massive hemorrhaging, and death would come quickly, at least by predation standards. Fossil evidence from the La Brea tar pits in Los Angeles, where thousands of Ice Age animals became trapped over millennia, shows that Smilodon often broke their canines. These teeth, while formidable, were also fragile, unable to withstand twisting or hitting bone. A broken fang would have been disastrous for a predator so dependent on them. Yet many Smilodon survived with broken fangs, suggesting they lived in social groups where injured individuals could scavenge from kills made by pride mates. Another predator, the scimitar-toothed cat or Homotherium, had shorter, more serrated canines and a body built more for pursuit than ambush. Its limbs suggest it could run well, unlike the more heavily built Smilodon. It likely hunted in open country, chasing down prey over distance. Some evidence suggests Homotherium specialized in hunting young mammoths, as juvenile mammoth remains have been found in a cave den in Texas associated with Homotherium bones. Dire wolves, larger and more robust than modern grey wolves, hunted in packs across the plains and forests of North and South America. At the La Brea tar pits, dire wolf remains outnumber all other carnivores, with over 4,000 individuals recovered. This suggests they were abundant and possibly more social than modern wolves, perhaps forming larger packs. Their teeth were adapted for crushing bone, suggesting they scavenged as well as hunted, able to consume parts of carcasses that other predators left behind. American lions, larger than African lions today, with males possibly exceeding 250 kilograms, stalked the grasslands. Despite their name, recent genetic evidence suggests they were more closely related to cave lions of Eurasia and may have been the same species. Cave paintings from Europe show cave lions without manes, suggesting American lions may have been similar, an adaptation to prevent overheating during hunts, or perhaps an indication of different social structure. Short-faced bears standing over 3 meters tall on their hind legs and weighing over 800 kilograms were among the largest land predators ever. They had relatively long legs and short faces, suggesting they were more cursorial, capable of running down prey than modern bears. Their size and build have led to debate about whether they were active predators or primarily scavengers, using their size to intimidate other carnivores and steal kills. Probably, like modern bears, they were opportunistic, eating whatever they could get: plants, animals, carrion, using different strategies depending on circumstances. And these are just the charismatic megafauna of North America. South America had its own unique assemblage: terror birds, flightless predators standing up to 3 meters tall, survived until perhaps 2 million years ago, hunting with massive skulls and powerful beaks that could crush bone. giant anteaters larger than modern ones, capybaras the size of small cars. And when the land bridge between North and South America formed about 3 million years ago, allowing the Great American Interchange, species from both continents mixed, leading to a surge in diversity and the extinction of some lineages unable to compete with newcomers. Eurasia had woolly rhinoceroses with thick fur and 2 horns, the front one potentially over a meter long, used to sweep snow aside in search of food. Cave bears, larger than modern grizzlies, hibernated in caves across Europe, leaving behind vast accumulations of bones. Giant deer, often called Irish elk, though they ranged across Eurasia, carried antlers spanning up to 3.6 meters, the largest of any known deer. Male deer grew and shed these enormous structures annually, a tremendous investment of energy that speaks to their importance in mating competition. Australia, isolated from other landmasses, had evolved its own unique megafauna, all marsupials. Diprotodon, the largest marsupial that ever lived, looked like a giant wombat 3 meters long and weighing over 2 tons. Thylacoleo, the marsupial lion, had the most powerful bite of any mammal for its size and blade like teeth for shearing flesh. Giant kangaroos stood over 2 meters tall. Megalania, a giant monitor lizard, grew over 5 meters long, making it one of the largest terrestrial lizards ever. Most of these went extinct around 50,000 years ago, shortly after humans arrived, though some may have persisted until 30,000 years ago. The ecosystems these animals inhabited were equally diverse. Mammoth steppe, a unique habitat that doesn't exist anywhere today, covered vast areas from Spain to Canada across the northern hemisphere. It was neither typical grassland nor tundra, but something in between, a highly productive mixture of grasses, sedges, and flowering plants with scattered shrubs. Cold, but not as cold as modern tundra, dry but with periodic moisture from melting snow. It supported enormous biomass of large herbivores, possibly greater per unit area than any terrestrial ecosystem today. Further south were mixed forests of pine, spruce, oak, and other trees, interspersed with meadows and river valleys. Wetlands and shallow lakes provided rich feeding grounds. Coastal areas, now mostly submerged, had productive estuaries and kelp forests. Mountain ranges had their own elevation-based zones, from valley floors to alpine meadows to barren peaks. All of this created a world of tremendous biological richness, a planet covered with giants, not just in a few isolated places, but globally. Every continent except Antarctica supported megafauna. And they weren't rare or exotic. They were the dominant component of their ecosystems, the most visible, the most impactful, the shapers of landscapes through their feeding and movement. This was the world into which early humans were born. Not a world waiting for us, empty and pristine, but a world already full, already ancient, already complex beyond imagination. A world where humans were not yet the dominant force, not yet the shapers of environments. We were just another animal, clever perhaps, but vulnerable, smaller than most of the megafauna, slower than the predators, less powerful than almost everything around us. And yet, we persisted, we adapted, we learned. And slowly, almost imperceptibly at first, we began to change from one more species in a crowded ecosystem into something different. Something that would, in time, transform the planet as profoundly as the first photosynthetic bacteria or the asteroid that ended the dinosaurs. But we're not quite there yet. We need to understand who we were before we became who we are. When we talk about early humans, we need to be careful about what we mean. The genus Homo, our genus, has existed for roughly 2.5 million years, but for most of that time, we were very different from modern Homo sapiens. We were smaller-brained. We had less sophisticated tools. We didn't have language as we know it, or art, or symbolic thought. We were, in many ways, just another species of primate, trying to survive in a world full of predators and competitors. The earliest members of our genus, like Homo habilis, appeared in Africa around 2.3 million years ago. They were still quite ape-like, standing only about 1.3 meters tall with long arms relative to their legs, suggesting they still climbed trees regularly. Their brains were larger than earlier Australopithecines, about 600 cubic centimeters compared to 400, but still less than half the size of modern human brains. Yet they made simple stone tools, flaked rocks, that could be used for cutting meat and scraping hides. These Oldowan tools, named after Olduvai Gorge in Tanzania, where many were found, represent a crucial threshold. They're evidence of planning, of understanding cause and effect, of teaching and learning. Tool use exists in other animals, but systematic toolmaking is rare. By 2 million years ago, Homo erectus had evolved. Taller, with larger brains of around 900 to 1100 cubic centimeters, and more advanced tools, they were the first humans to leave Africa and spread into Asia and Europe. Fossils of Homo erectus have been found in China, where they're sometimes called Peking man, in Indonesia as Java man, and in the Caucasus Mountains at Dmanisi in Georgia. They controlled fire, a technological achievement that can't be overstated. Fire provided warmth in cold climates, extended the day by providing light after dark, protected against predators, and most importantly, allowed cooking, which made nutrients more accessible and may have been crucial for supporting larger brains. They built shelters, simple structures of branches and hides. They likely had some form of proto-language, though nothing like modern speech, perhaps a vocabulary of a few dozen words and simple gestural communication. For over 1 million years, various species of Homo coexisted in different parts of the world, each adapting to local conditions, each developing their own tool traditions and survival strategies. In Europe and Western Asia, Neanderthals evolved around 400,000 years ago, a separate species from modern humans, but closely related, our closest extinct relatives. They were stocky and powerfully built, an adaptation to cold climates with shorter limbs to reduce heat loss, and shoulders and hips built for tremendous strength. Their brains were as large as or larger than ours, averaging about 1,400 cubic centimeters. They made sophisticated stone tools using the Levallois technique, a method that required planning and skill to prepare cores and strike off precisely shaped flakes. They hunted large game, working together to bring down mammoths, woolly rhinos, and bison using thrusting spears. They built dwellings, not just natural shelters but constructed huts. They cared for their sick and injured, as evidenced by fossils showing healed injuries that would have been debilitating, indicating others provided food and care. They buried their dead with apparent ritual, sometimes placing items in graves, though the interpretation of these burials is debated. They even made jewelry and used pigments, suggesting some capacity for symbolic thought. They were not the primitive brutes of popular imagination. They were intelligent, capable people, adapted to their environment in ways we've only recently begun to appreciate. In Asia, other human species evolved in isolation. Homo floresiensis, discovered on the Indonesian island of Flores, stood only about 1 meter tall, with brains of just 400 cubic centimeters, yet survived until as recently as 50,000 years ago, living alongside modern humans for a time. The Denisovans, known mostly from DNA rather than fossils, lived in Siberia and interbred with both Neanderthals and modern humans, leaving genetic traces in modern Asian and Oceanian populations. Meanwhile, in Africa, our own species, Homo sapiens, evolved. The earliest fossils date to about 300,000 years ago from Jebel Irhoud in Morocco, showing a mix of archaic and modern features. For most of that time, we weren't particularly special or successful compared to other human species. We looked different, lighter built, with higher foreheads, smaller faces, and more prominent chins. But behaviorally, for the first 200,000 years of our existence, we weren't obviously superior to Neanderthals or other contemporary humans. We used similar tools, hunted similar prey, lived in similar ways. The real transformation, what some archaeologists call the Upper Paleolithic Revolution, or the Great Leap Forward, happened much more recently, perhaps 50 to 40,000 years ago, though the timing varied across regions, and the change may have been more gradual than the term revolution implies. That's when we start seeing clear evidence of fully modern symbolic thought and complex culture. Cave paintings, first appearing around 45,000 years ago in Indonesia and Spain, show sophisticated understanding of perspective, composition, and representation. The paintings depict animals with stunning accuracy and sometimes include abstract symbols, handprints, geometric patterns, suggesting systems of meaning we can only guess at. Carved figurines, the oldest known is the Venus of Hohlfels from Germany, dated to about 40,000 years ago, show attention to detail and artistic sophistication. Jewelry made from shells, teeth, and carved bone appear in the archaeological record. Musical instruments, including bone flutes, show appreciation for sound and rhythm beyond mere survival needs. Complex tools made from bone and antler, including needles for sewing fitted clothing, harpoons for fishing, and atlatls for throwing spears with greater force, demonstrate innovation and specialization. Evidence of long-distance trade networks shows that groups were interacting across hundreds of kilometers, exchanging materials and perhaps ideas. All the markers of a fully modern human culture, one we would recognize as fundamentally similar to our own despite the technological differences. But even then, even with all our cleverness and creativity, we were still living in a world dominated by megafauna. We hunted mammoths when we could, using coordinated group tactics, driving them into traps or over cliffs. We scavenged from saber-toothed cat kills. We competed with dire wolves and hyenas for carcasses. We lived in caves when we could find them, built shelters of mammoth bones and hides when we couldn't. We followed migrations of reindeer and bison. We gathered plants and fished in rivers and along coasts. Our population was small. Estimates suggest that even at the end of the Pleistocene, there were probably only a few million humans worldwide, most of them in Africa and southern Asia. We lived in small bands of perhaps 20 to 50 individuals, extended family groups that cooperated for survival. We didn't farm. We didn't keep animals. We had no permanent settlements. We moved with the seasons and the availability of food, carrying everything we owned on our backs. This way of life, hunter-gatherer nomadism, was the only way humans had ever lived. It had been our existence for hundreds of thousands of years, our ancestors for millions, and there was no reason to think it would ever change. No vision of what might come, no plan, no destination, just survival, day by day, season by season, generation by generation. The world around us was stable in the only ways that mattered. The climate fluctuated between glacial and interglacial periods, but these changes happened so slowly that individual humans never noticed. The megafauna had been there since before anyone could remember and seemed eternal. The plants and landscapes were familiar, passed down through oral tradition and direct observation. This was how the world was, how it had always been, how it always would be. And then, everything changed. Around 12,000 years ago, something happened. The exact timing varies by region, but across the world, particularly in the Americas, a wave of extinction swept through the megafauna. Species that had thrived for millions of years vanished in what is, geologically speaking, an instant. In North America alone, over 30 genera of large mammals went extinct. Mammoths, mastodons, giant ground sloths, saber-toothed cats, dire wolves, American lions, American cheetahs, horses, camels, all gone. In South America, the loss was even more dramatic. In Australia, which had already lost its megafauna thousands of years earlier, the pattern was similar. Even Europe saw significant extinctions, though less severe than in the Americas. What caused this? The question is still debated, and the answer is probably complex, involving multiple factors. But two main hypotheses dominate the discussion among researchers. The first is climate change. The end of the last glacial period, around 11,700 years ago, was marked by rapid warming. Ice sheets retreated, sea levels rose. The mammoth steppe, that unique and productive grassland tundra ecosystem, disappeared, replaced by forests in some areas and less productive tundra in others. For animals adapted to the mammoth steppe, this shift would have been catastrophic. Their habitat vanished, food became scarce, populations declined. But climate change alone seems insufficient to explain the extinctions, at least to many researchers. Large animals had survived previous interglacial periods without such devastating losses. Something was different this time, and that something, many researchers believe, was us. The second hypothesis is human hunting. As human populations grew and spread, and as our hunting technologies improved, we may have hunted many megafauna species to extinction. This is called the overkill hypothesis, and it's supported by several pieces of evidence, though it remains controversial. First, extinctions closely followed the arrival of humans in different regions, suggesting a connection. In North America, humans arrived perhaps 13 to 15,000 years ago, and megafauna extinctions peaked shortly after. In Australia, humans arrived perhaps 50 to 60,000 years ago, and megafaunal extinctions occurred within a few thousand years. In Madagascar, humans arrived only about 2,000 years ago, and the island's giant lemurs, elephant birds, and other large animals promptly disappeared. The correlation is striking, though not conclusive. Second, the animals that went extinct were mostly large-bodied species. Smaller animals, which breed faster and are harder to hunt, survived. This pattern is consistent with hunting pressure rather than climate change, which would be expected to affect large and small species more equally. Third, there is direct archaeological evidence of humans hunting megafauna. Mammoth bones with stone tool-cut marks. Kill sites with the remains of multiple animals processed for meat. Spear points found embedded in mastodon skeletons. We know humans hunted these animals. The question is whether we hunted them to extinction, or whether hunting combined with other factors to push vulnerable populations over the edge. The truth is probably somewhere in between. Climate change stressed megafauna populations, reducing their numbers and making them more vulnerable. Human hunting, even if relatively light, could have been enough to push populations already in decline over the edge. Large mammals reproduce slowly. A female mammoth might have only 4 or 5 offspring in her lifetime. If hunters killed more mammoths each year than were being born, populations would decline inexorably toward extinction, even if the hunting pressure seemed sustainable in the short term. There's also evidence of a third factor, one that's more speculative but intriguing. Around 12,800 years ago, at the beginning of a cold snap called the Younger Dryas, there appears to have been a major extraterrestrial impact, possibly an airburst from a fragmenting comet. Evidence includes a layer of sediment rich in microscopic diamonds and other impact markers found across North America and Europe, though this hypothesis remains debated and not all researchers are convinced. Such an event could have triggered wildfires, disrupted ecosystems, and contributed to both climate change and population crashes, though its role in the extinctions is uncertain. Whatever the cause or combination of causes, the result was unambiguous. The world's megafauna, the giants that had dominated ecosystems for millions of years, were gone. And the landscapes they left behind were fundamentally altered. Without mammoth herds to keep grasslands open by grazing and trampling, forests encroached. Without large herbivores to disperse seeds and nutrients, plant communities changed. Without mega herbivores, predators that specialized in hunting them disappeared too. The world became emptier, quieter, and humans, who had been one species among many, suddenly found themselves with less competition, more resources, and more freedom to shape environments to their needs. It was not intentional. We didn't plan to eliminate the megafauna. We probably didn't even notice it was happening until it was done. But the consequences were profound. This moment, this transition from a world full of giants to a world dominated by smaller species and increasingly by humans, marks a threshold. It's not yet the beginning of civilization, but it's the precondition for it. Because without the megafauna extinctions, what came next might never have happened. After the megafauna extinctions, but before the rise of agriculture, there was a brief window, perhaps 1,000 or 2,000 years, when humans lived in a world that was neither the Ice Age wilderness of their ancestors nor the agricultural landscapes of their descendants. This was the Mesolithic in Europe and the Middle East, the Archaic period in the Americas, a time of transition. The climate was stabilizing into the warm, interglacial period we still live in today, called the Holocene. The ice sheets had retreated, sea levels had risen to near modern levels, flooding coastal areas and creating new shorelines. The mammoth steppe was gone, replaced by forests and grasslands. The megafauna were mostly extinct, but other animals, deer, elk, bison, smaller predators, were abundant. Humans during this period were still hunter-gatherers, but they were becoming more settled. With the megafauna gone, people focused on smaller game, on fishing, on gathering nuts and seeds. In some places, particularly in the Middle East, and later in China and Mesoamerica, they began to intensively harvest certain plants, returning to the same locations year after year as the plants ripened. These weren't domesticated plants, not yet, but the relationship between humans and certain species was becoming closer, more dependent. Archaeological sites from this period show evidence of semi-permanent settlements, circles of post holes indicating houses, trash pits and storage facilities, cemeteries, suggesting that groups were staying in one place long enough to bury generations of their dead together. Social structures were becoming more complex. Trade networks were expanding. Art and symbolic thought were flourishing. But still, no agriculture, no cities, no civilization in any sense we'd recognize. Just human groups living in a world that had become less dangerous, more predictable, and more amenable to a settled existence. The stage was set. All it would take was the final step, the transition to farming, and everything would change. That transition, when it came, was not dramatic. There was no invention, no sudden realization. In the Fertile Crescent of the Middle East, people began planting seeds they'd gathered, deliberately cultivating wild wheat and barley. Over generations, through repeated planting of the largest seeds and most productive plants, these wild grasses were gradually transformed into the first domesticated crops. Sheep and goats, which had been hunted, were captured and bred in captivity, becoming the first domestic livestock. Similar processes occurred independently in China with rice and millet, in Mesoamerica with maize and beans, in South America with potatoes and quinoa, in New Guinea with taro and banana. Each region had its own set of plants and animals that lent themselves to domestication, and in each region, over hundreds or thousands of years, hunter-gatherers became farmers. This agricultural revolution, as it's often called, was the true beginning of civilization. Because once you farm, you stay in one place. You build permanent houses. You accumulate possessions that you don't have to carry. You can support a larger population in a smaller area because farming produces more food per acre than hunting and gathering. And with a larger settled population comes division of labor. Not everyone needs to farm. Some can become craftspeople, traders, priests, rulers. Social hierarchies emerge. Writing systems develop to keep track of harvests and taxes. Cities form. Within just a few thousand years of the adoption of agriculture, the first civilizations appeared. Sumer in Mesopotamia, Egypt along the Nile, the Indus Valley Civilization in South Asia, the Shang Dynasty in China. And from there, the story becomes the history we know. Empires rise and fall, technologies advance, art and philosophy flourish, humanity spreads across the globe, reshaping every ecosystem to suit its needs. But all of this, every single bit of recorded human history, every city ever built, every book ever written, every war ever fought, all of it happens in just the last tiny sliver of time. 10,000 years, 12,000 at most, a nothing span compared to what came before, a fraction of a percent of Earth's existence. And so we find ourselves here at the end of this journey backward through time. We've gone from the present, from the world of cities and technology and civilization, back through the age of early humans, back through the age of megafauna and ice, back through the age of dinosaurs, back through the eons of simple life and frozen planets and molten rock, all the way to Earth's fiery birth 4.5 billion years ago. It's a lot to take in. And if you're feeling a little disoriented, a little unmoored, that's appropriate. Because the lesson of deep time, if there is one, is perspective. We are so recent, so brief. The entire span of human existence, not just civilization, but the entire genus Homo, is less than 0.1% of Earth's history. Modern humans, people like us with brains and languages and cultures that we'd recognize, have been here for maybe 300,000 years. That's less than 0.07%. And yet, in that infinitesimally small window, we've become one of the most transformative forces the planet has ever seen. We've reshaped landscapes. We've driven countless species to extinction. We've changed the composition of the atmosphere and the chemistry of the oceans. We are, right now, in this moment, leaving a geological signature that will be visible millions of years from now to whatever beings, if any, come after us. We've become a planetary force in the blink of an eye. That's humbling and terrifying and awe-inspiring all at once. Because on one hand, it shows how powerful we are, how quickly intelligence and technology can transform a world. But on the other hand, it shows how little time we've had to learn wisdom, to understand the consequences of our actions, to develop the foresight necessary to manage the power we've gained. The age before civilizations was not a paradise. It was brutal and dangerous. Life was short. Death from starvation, disease, predation, and exposure was common. There's no romanticizing the past here, but it was also stable, at least on human timescales. The ecosystems that existed at the start of the Pleistocene were largely the same at the end, apart from the extinctions humans may have caused. For hundreds of thousands of years, our ancestors lived in roughly the same way, using roughly the same tools, in roughly the same environments. Then, in the last few thousand years, everything accelerated. And we went from one more animal in a crowded world to the dominant species on the planet, the only one with the capacity to deliberately choose what kind of world we want to live in and what kind of world we'll leave behind. That choice is still ahead of us, or perhaps it's happening right now in every decision we make, collectively and individually, about how we live, what we consume, how we treat the other species we share the planet with. We stand at a threshold not unlike the one our ancestors stood at 12,000 years ago, when the megafauna were vanishing and the world was becoming something new. Except this time, we're aware of it. We have science and history, and the ability to look forward and imagine what might come. Will we choose well? I don't know. No one does. But I think it helps sometimes to remember where we came from. To remember the incomprehensible vastness of time that preceded us. To remember that we are not separate from nature, but part of it. A recent branch on an ancient tree that's been growing for billions of years. To remember that the Earth was here long before us and will be here long after, in some form, regardless of what we do. That's not an excuse for inaction or indifference. If anything, it's the opposite. Because knowing how rare and precious this moment is, how unlikely our existence is, how brief the window of time we have to experience this world and shape its future, should make us cherish it more, not less. Should make us think harder about what we're doing and why. Should make us want to be worthy of the long, strange, beautiful journey that brought us here. And maybe, just maybe, understanding deep time can help us think in longer spans. Not just about the next quarter or the next election, but about the next century, the next millennium, the deep future that will, if we're lucky and wise, be as vast as the deep past. Because we're part of a story that didn't start with us and won't end with us. And the most meaningful thing we can do is try to be good ancestors to whoever or whatever comes next, just as we're the beneficiaries of everything that came before. So if you made it this far, thank you. Thank you for taking this journey through time with me, for letting your imagination stretch across eons and continents and extinctions and ice ages. If this resonated with you, if it made you think or wonder or feel something, I'd be grateful if you tap the like button or subscribe to the channel. It helps this content reach other curious minds who might appreciate it. And now, as we come to the end, I hope you can rest a little easier. The questions are still there. The mysteries remain. But perhaps there's some comfort in knowing that we're part of a much larger story. One that's been unfolding for billions of years and will continue long after we're gone. A story of transformation and adaptation, of life persisting and evolving and finding ways forward even in the face of catastrophe. A story that includes mammoths and saber-toothed cats and dinosaurs and ancient seas and frozen planets and countless other wonders we'll never know about because time has erased them. We're here now, in this moment, part of the story, and that's extraordinary. Sleep well, time traveler. Dream of ice and giants and worlds that were. And when you wake, remember that you're living in the age that comes after the age before civilizations, in the brief window when humans became something new, something unprecedented. What we do with that window is up to us. And that's both a responsibility and an opportunity, unlike any that's ever existed in the 4.5 billion year history of this planet. Good night.